We talked about interference kind of conceptually with a little bit of math, but now let's do out some detailed math to really understand this. And this might make more sense to you, but again, it actually confirms what we did graphically and conceptually before. So we can imagine that we have one overall displacement that we want to find by summing up the two displacements from our individual waves. And an easy way to think about that is to define one phase for each of them. Now again, this phase is going to vary in space and time, but because these share a wavelength and we're not actually changing anything in time, this can make a lot of sense. Notice that for simplicity, we are talking about these having the same wavelength, same amplitude. It isn't something that is required, it just simplifies the math. So when we expand out what that individual phase is, we again remember that we have x1 and x2 corresponding to one point in space being different distances from each of our sources, maybe. And again, phi sub 10, phi sub 20 represents that we have different initial phases for each of these. So again, we're just trying to find our overall displacement, which comes from summing up the terms from two different waves. There's a really helpful trig identity to use here, and really this is the entirety of the math. And this comes from actually kind of working backwards from this one. But so if we're adding up two different sine waves, we can express it as a cosine multiplied by a sine. If you said, how on earth would I know to do that? Well, the good news is the book does this for you and tells you you can do this. I'm never going to ask you to magically derive something like this on a test in intro physics. So we need to use this identity, noticing that alpha in this case is this entire thing. Beta is this entire thing. So when we subtract them, we see that omega t is going to cancel out since they in fact have the same thing. But when we add them, omega t isn't necessarily going to cancel out because it's shared. So again, we have a cosine term and a sine term. So now this is what we get. Again, we have a 2 coming from just the trig identity. A is our overall amplitude that our original waves had. And now we have this cosine term. And notice that it is delta phi over 2. And in this case, this is not going to be just our initial phi. This is the total phi. So this I think is a little bit tricky. Remember that this is coming from these, and that's what is up here. But when you actually subtract these, omega t is falling out. So this has both x and phi not in it, but not t. Then you have sine of some stuff where there's still a kx and an omega t, and then this phi naught average. So both of these averages are simply coming from the sum of the two values that appeared up here, dividing by 2. So what's interesting about this, again, this was just some math, is that this still has the form of a traveling wave, right? So we still have a traveling wave after we've summed up two individual waves. But then we have this new thing over here that is basically just your amplitude. And notice that this amplitude does not depend on time, and it's really just kind of a constant value. So we have amplitude multiplied by a traveling wave. So when we have two waves interfere, we just get a new traveling wave. So this is that amplitude function, and we can think about just what its magnitude is rather than worrying about the absolute sign. So if we have the maximum value, that is when you have cosine of something gives you 1. And that would be actually m times 2 pi. So you're going to get your maximum values at 0, pi, 2 pi, and so on, but there's a 2 on the bottom. So that's where we can just say it's m times 2 pi. Now we get a 0 for this whole thing, again for A, if what's on the inside is going to be m plus 1/2 times 2 pi. Now, this is actually what we got before when we were talking about phase differences, thinking in terms of initial phase and path length. So this is not a new result. This is actually the identical result to what we had in the previous section, where we got it kind of just qualitatively rather than thinking mathematically and getting it this way. What's helpful about doing it this slightly more complicatedly mathematically way is that we can talk now about other types of phase differences. So the blue line represents our sum, the red and the green line represent our different traveling waves. Remember that the blue line would also be a traveling wave here, so this is one snapshot in time. So we get different phase differences. All three of these situations are not the maximum value or the zero value, i.e. they are not perfectly constructive or perfectly destructive. And again, before I said that the perfectly constructive interference is really a special case, that you only get it sometimes. Destructive or perfectly destructive interference, you only get that sometimes. For lots of other angles, you get something in between. Your sum is still a sine wave, and the amplitude could be less than your initial amplitude, right? These are close to being 180 degrees, or pi, out of phase, but they're not quite there. When they're only 40 degrees from each other, that's still kind of close to zero, but again, we're not all the way up at 2. 90 degrees out of phase actually gives us square root of 2 times our original amplitude. So just try to understand a little bit of where this is coming from. But again, there's kind of a mathematical argument to get here, and we can then do any type of interference, any phase difference, not just the special cases of constructive and destructive interference.